Welcome back. In this segment, we'll be studying Chapter 4, which deals with discrete random variables. Well, at this point, you are experts of determining what discrete random variables are, and these are random variables that deal with data that we count. So we would count as in the discrete case. For example, you might be interested in counting the number of stamps that you use per month so that you can go ahead to the post office and order a certain number of stamps. Or you might be interested in counting the number of pesky telephone solicitors that call while you're trying to eat dinner. Now, you could also count the number of days it rains during a season. If you were interested in the rainfall, though, that would be continuous data, not discrete data. With discrete random variables, each data value has a probability from 0 to 1 inclusive, meaning it could be 0 or up to 1, of happening. And if we sum up all the possibilities, all the possible values, our total will be 1. This is called a PDF, or probability distribution function. So I'm going to start by looking at an example here. Suppose that Jan goes to the juice club after school sometimes, and the probability that she goes 0 times per week is 20%. The probability that she goes 1 time per week is 40%. The probability that she goes twice per week is 30%. And the probability that she goes 3 times per week is 10%. She never goes more often. Now, the first question you might think or come up with is, how do we know these probabilities? These would be the probabilities that are determined from surveying week after week after week of following Jan and seeing does she go to the juice club or not. Now, she might be interested in this because she might want to know how much money should I bring, or should I pack a lunch, and so on. Well, we start now with a new concept, and this is our random variable, capital letter X, and this is what is it that we're counting. In this case, we're counting the number of days Jan goes to the juice club after school per week. So we would add the number of days Jan goes to the juice club, I'll just put JC for a juice club, after school per week. So we're counting. Here we're counting the number of days Jan goes to the juice club after school per week. Lowercase x are the values that the random variable can take on. Okay, so let's look at this now. Let's see what the values are. Well, it says that she goes 0 times per week 20% of the time. So one of the values is 0. She goes 1 time per week, 40% of the time, so one value is 1. She goes twice per week, 30% of the time, so we have 2 and 3. Now, keep in mind, I guess we could have 4, 5, 6, 7, but it says she never goes more often. So if we did have 4, 5, 6, 7 as possible values, the probability of those happening would be 0. If we add up the probabilities of each of these occurring, we would get 1. For example, 0.2 plus 0.4 plus 0.3 plus 0.1 equals 1, or 100%. The next thing we're going to do is we're going to make a table to summarize this data. And so we're going to start this table, and I'm going to have the value of x and the probability that x occurs. So the different values that we have, let's see. We could have x is equal to 0, and the probability we saw was 0.20. X could be equal to 1, and the probability is 0.40. X could be equal to 2, with a probability of 0.30. And x could be equal to 3 with a probability of 0.10. So if we were to add up these probabilities, 0.2 plus 0.4 plus 0.3 plus 0.1, we know we get 1 or 100%. And that's why if we really wanted to, we could extend the chart to the 7 days of the week because the probabilities next to them would just be 0. Well, maybe what we are interested in is the probability of her going a certain number of days, but more likely this is not what we're interested in. More likely we're interested in, on average, how many times per week does she go? What's the long-term average? Now we know for any given week she can only have the values 0, 1, 2, or 3, but on average. Now, why would she want to know the average? One possibility is maybe she's working out a budget and she needs to know how much should she put in her juice club budget. Well, some weeks she goes more than others, but if she knows the average number of times she goes per week, she can figure out the average time times the cost and figure out how much money she should put into her budget. Well, I'm going to do a quick review here of Chapter 2 of probability, or actually Chapter 3 of probability. And I just want to remind you, one way of figuring out probability was to have the probability as the number of times that something happened over the total number of times that we have. And so one possibility for probability is the probability is equal to the frequency divided by the total number. This would be F over N. One way of determining probability is the frequency divided by the total number. Now, we didn't do this on the tape, but in the textbook you hopefully read the part in Chapter 2 about the population average. The formula for the population average is to take each different value of x, multiply by its frequency. So the first value of x times its frequency, the second value of x times its frequency, and so on. And then this capital sigma means add them all up and divide by the total number that we had. So this was the definition of the population average from Chapter 2. Well, the key here is to figure out what's a constant and what numbers are changing. Well, n is a constant, x is changing, and within each x the frequency changes. So because x is a constant, now I'm not expecting that you're going to give me a proof to show me this again. I just want you to see where this is derived from. Because x is a n is a constant, we can bring the n inside here. And so now we have the summation of x times f over n. In addition, we can manipulate it more, and we get the population average equals the summation of x times frequency over n. Well, remember, frequency over n is just the probability. Probability of x equals frequency over n. So we can replace this f over n with probability. And here we get the formula for the probability of x occurring right in here. And so we take each probability multiplied by the value of x. Then we add those all up, and we'll get what is the long-term average, or our expected value. All right, so we're going to go back to this example that we just did with Jan going to the juice club and try to figure out what is her long-term expected average. On average, how many times per week do we expect that Jan will be going to the juice club? So I have back up here her chart. All right, back to the Jan example here. Find the expected number of times per week that Jan goes to the juice club on average. This part of the chart we already had. This part we already had. Now, let's see how we can get this part. Remember, the mean, the long-term average, is the summation, meaning adding all up, each value of x times the probability that that value occurs. And in some textbooks, you'll see x times the probability that the random variable equals x. This is sort of the official way of writing this, and this is a little bit of a shortcut right here. The same thing right here. Probability that the random variable x takes on this lowercase value. All right, now how we got the first one? 0 times the probability of 0 occurring. The probability of 0 occurring is 0.2. 0 times 0.2 equals 0. Not too hard there. 1 times the probability of 1 occurring. 1 times 0.4 1 times 0.4 equals 0.4. 2 times the probability of 2 occurring. So 2 times 0.3 equals 0.6. 3 times 0.10 equals 0.3. And so now what we've done is we've done part of the formula which said take each value of x, multiply it by its probability, and we made this column. And now we add them all up. That's the last part. So we add 0 plus 0.4 plus 0.6 plus 0.3, and we get 1.3. Now what this means is that on average of studying Jan week after week after week after week, we would expect her long-term average per week to be about 1.3 times per week. On any given week, she can't go to the juice club 1.3 times. On any given week, she can go 0, 1, 2, or 3. But on average, over the long term, we would expect 1.3 times. This is also done with expected winnings and expected earnings. Let's look at one other example. Let's say you're going to enter some sort of a gambling part, and you could win. We'll let x equal your winnings. If you're correct, you could win $100, and if you're incorrect, you have to pay $50. So your values are x, and x takes on 100, and x takes on negative 50. So again, we would make a table. Our values, negative 50 and 100, and we would fill in the probabilities. And then if you wanted to find out what's the probability that I come out winning, you would have to multiply across and add them all up. If your expected value were a positive number, then you would expect to come out ahead. If your expected value is a negative number, you would expect that your winnings would be a loss on average over the long term. We're going to go on to a specific type of discrete distribution now, and this deals with events that have the same probability of happening every single time. We have a set of trials called Bernoulli trials, and these were developed. There's a very famous family of Bernoulli mathematicians in the 16 and 1700s, and a Bernoulli trial is a trial that has two outcomes. You could either succeed or you could fail. And the probability of succeeding is going to be the same every time you do the experiment. So every time you do the experiment, the probability that you succeed will be the same. Every time you do experiment, the probability that you fail will also be the same, meaning that this will stay constant from time to time to time. And there are only two outcomes, success or failure. So let's think about some examples of this. If you roll a die and you record what number is showing, you have 6 outcomes, 1, 2, 3, 4, 5, 6. Even though every time you roll, each roll is independent from the others, you would not consider this to be Bernoulli trials. If you roll a die and you're interested if the outcome was an odd number or an even number, then you would have Bernoulli trials. Each roll is independent from each other, and the probability of rolling an odd number stays the same every time you roll. Now, one specific distribution that uses Bernoulli trials, it's what's called the binomial distribution. And in the binomial distribution, we're counting Bernoulli trials. We're doing several Bernoulli trials, and we're counting the number of successes that we have. The notation is the number of trials is equal to n. The probability of success is p. Now, if you don't succeed, you could fail. And the probability of failure is 1 minus the probability of success. Success and failure are complements of each other. What we're counting is the number of successes. And if you do a trial n times, you could have 0 successes, 1, 2, 3, up to n successes. So the most number of times you could succeed is the number of times you do the experiment. The notation that we use for a binomial distribution is x follows or takes on, capital B is the standard notation, binomial distribution, with n and p as the parameters that we're interested in, n being the number of trials and p being the probability of success on each trial. And these numbers we fill in. Once we fill in, we can do any calculations. All right, here's an example. At the fencing center in San Jose, and if you don't know about the fencing center, this is not for fencing posts, this is for the martial arts of fencing, and this is one of the best fencing places around in the state, actually, with some world champions teaching there. 60% of all fencers use the foil as their main weapon. So there are 3 weapons for fencing: the foil, the saber, and the epee. About 60% at this place use the foil. We randomly survey 25 fencers at the fencing center. I just abbreviated it. We are interested in the number that do not use the foil as their main weapon. Okay, so we have the fencing center. We're going to randomly survey 25 of them. And we're going to say, do you use the foil or do you not use the foil as your main weapon? A success, then, we're counting the number that do not use the foil. The random variable now is the number that do not use the foil as their main weapon. That would be a success. We're surveying 25 fencers. So the least number that could say, I do not use the foil, is 0. Or the next one is 1 or 2 or 3 up to 25. Now this is discrete because we're counting. We're counting the number of successes, 0, 1, 2, 3, up to 25. The distribution for x now. The next thing we want to do is state the distribution. The distribution for x is going to follow the binomial distribution. And so see, I put in the 25 for n. And p, in this case, we're interested in the number that do not use the foil. If 60% do use the foil, 1 minus 0.60 gives us 0.4. 40% do not use the foil as their main weapon. Okay, now let's do some calculations with this. The next thing we want to be able to, I'll leave the problem up here while I'm getting the next set. The next thing we want to be able to do is come up with some calculations. And we're going to use our calculator for this. The probabilities involve permutations and combinations, and some of you may have studied this in the past. If you want to use the formulas, you can, but I don't recommend it since the technology makes it easier for us. So the first thing we're going to do now is find the expected number that do not use the foil as their main weapon. All right, well, we have 25 people who we're surveying. And of the 25, 40% do not use the foil. So we're expecting at least that 40%. So 25 times 0.40 would be 10. We would expect that 10 of those 25 people would not use the foil, since 40% of the whole club doesn't use foil as the main weapon. Find the probability that exactly 6 do not use foil as their main weapon. So we're looking for the probability that x is exactly 6. Now we're going to get on the calculator and do it on the calculator. And hopefully you've gone through the instructions in the workbook for using the distributions. But I'm going to put this up here now, and we'll zoom right in here. Okay, and we want the probability that x is equal to 6. So we're going to go into the distributions, which is right here. Distributions, DISTR. And we have second distributions. And we're looking down for binomial. Here's the normal, which we'll get to in Chapter 6. The student t in Chapter 8. And at the chi-square. We're getting here. Okay, now here we have our discrete distributions. Oops. Here we are. Binomial, it's right over here. Binomial, PDF and binomial CDF. What the binomial PDF gives us is the probability that x is exactly a value. What the binomial CDF is a cumulative probability. Remember cumulative relative frequency from chapter 1? Well, this is a cumulative probability that x is less than or equal to some value. So we'll go into the PDF right here. And what we're looking for is the probability x is equal to 6. The notation that we put in is n, and then a comma, p, which is 0.4, and then the value that we're looking for, 6. Close the parentheses. And that gives us 0.0442. So this is the probability that x is exactly 6. If I did the other one, probability CDF, and we tried the same thing, and we had 25, 0.4, 6. The difference between the two, you see the P and the C, is that this would give us the probability that x is at most 6, meaning 0, 1, 2, 3, 4, 5, or 6. All right, let me look at the next problem. The next problem is find the based on numerical probabilities, I guess I'll have to widen this out here. Would you be surprised if all 25 did not use the foil as the main weapon? So in this case, we're now looking for the probability that x is equal to 25. The probability that x is equal to 25. So we're going to go into the binomial, back to the distribution, PDF, and find 25.4, 25, meaning x is 25, and we get, now look at this, I'll zoom this right in here. We have 1.1259 e negative 10. Hopefully you've realized that this is scientific notation. Computers and calculators use scientific notation when a number gets too big or too small. And so this is telling us that it's 1.1259 times 10 to the negative 10th. The E stands for 10 to the negative 10th. So this is 0.000000001. It's point followed by the decimal point, followed by 9 zeros, and then a 1, which when we round to 4 decimal places is about 0. So the question was, would you be surprised if all 25 picked did not use the foil? And because the probability of that happening is almost 0, we would say yes, we would be surprised. Okay, let me go on to just a couple more here, and then we'll close up for today. Find the probability that at most 15 do not use foil as their main weapon. So we're looking for the probability that x is less than or equal to 15. Now this time it's a cumulative. We could either add up the probabilities that x equals 0 plus the probability x equals 1 plus the probability x equals 2 all the way up to 15, or we could use the cumulative probability. And so I think I'll do that. I'll use the cumulative probability. So we're going to go in and put 25, 0.4, 15, and cumulative. Whoops, I made a mistake. Let's see where I made the mistake too. Oh, I forgot a comma here. I did a decimal point. All right. Binomial CDF, 25, 0.4, 15. And the probability that x is less than or equal to 15 is 0.9868. So this would be the probability that x is up to and including 15. One more, and then we'll wrap it up and stop for today's lesson, is to find the probability that 11 or 12 do not use the foil as their main weapon. Now we're looking for the probability that x equals 11 plus the probability x is 12. That's one way to do it. You could add these two individual probabilities. But another way to do it is to say, I'll take the cumulative probability of up to 12 and subtract out the cumulative probability of up to 10. and what will be left over is 11 to 12. So that's another way to do it. And you could do that one on your calculator also. All right, so today in this class, what we've done is we have looked at starting discrete distributions. We went and did examples with distributions that were discrete, that didn't seem to follow any set pattern, but we built the probability distribution function and found the long-term expected average, and then went on to the binomial distribution, which deals with having a certain number of trials and counting the number of times something occurs when the probability doesn't change. Now it's time for you to go home and work out the problems, and certainly to make sure you can use whatever technology you're using, whether it's a graphing calculator or a computer or just working these problems out using the formulas, that you can go and do it. And I'll be back with the next segment soon.